The 388th lecture meeting of Yomiuri International Economic Society. Our guest speaker today is Mr. Tetsuro Higashi, Chairman of the Board of the Directors of Rapidus Corporation, a semiconductor manufacturer. For his biography, please refer to the booklet in your hand. The theme of the lecture is Japan is Back, a renewed challenge at leading-edge semiconductors. Rapidus is aiming to mass-produce cutting-edge 2-nanometer semiconductors, which no other company in the world has ever achieved. With the aim of mass production around 2027, the company plans to begin manufacturing prototypes this April. As such, the year 2025 is dubbed the first year of 2 nano. How is Rapidus pressing ahead with this national project? Mr. Higashi will share his strategy over the next 50 minutes and take questions in the remaining time. Let me introduce myself. I will be your MC today. I am Takahashi, Senior Research Fellow at Yomiuri Research Institute. Now, let us start. Over to you, Mr. Higashi. Please come to the podium, Mr. Higashi. Please give him a big round of applause.
As has been kindly introduced, my name is Higashi, and I would like to thank all of you for sharing with me your valuable time. I didn't realize that so many of you, the leaders and dignitaries of the different industries and different sectors, have gathered. It is a great honor for me. Now, immediately, if I may go into the presentation, this slide shows when the Rapidus foundry is completed. This is the expected scene. It is surrounded by greenery, and on the top you can see the top of the roof is covered by greens as well, and the chips that we will be manufacturing here would be the gate all around. This is completely new structure, a structure, what we call GAA in short. And the outside, it is green all around, and this is also GAA, as you will be able to understand. So we would like to move forward with both GAAs. Now let me explain the background. On the left-hand side, as you can see, the chart at the top shows region by region market share of semiconductors as the vertical axis, and the horizontal axis shows the period, the years, from the late 1980s to 1990s, the middle of 1990s. Japan's market share was #1 in the world. We had about 50% share of the global market. So Japan has been leading the way up until then. But then from 1992 onwards, we have seen reversal. United States, especially Intel and other companies, have come to the fore and have grown dramatically with microprocessors at the core. And then we have gone into fabless process, especially in the United States. We have seen a dramatic increase of fabless semiconductor processes. So rather than a production, it will be more of a design and research, development, and so forth. And accordingly, the growth enjoyed was the foundries in Taiwan, which were concentrating on manufacturing, production. So there was a specialization, it seems, of the labor between the United States and other countries, especially Taiwan. And Japan, against this backdrop, we have lost our share dramatically. Our share right now is less than 10%. Not only this poor figure of market share, but Japan has concentrated on memory chips, the so-called logic chips. And for this, investments have actually stopped in Japan. Therefore, the cutting-edge technology has been lost by this country. So Japan was sort of suspended. And that has been the big problem. On the left-hand side bottom, you can see with this illustration that Japan used to be the leader in the market, and Japan has been contributing significantly. But Japan has been dropped from those cogs rotating. But if we can see more smooth import, especially the import in trade, if there are no obstacles, even though there could be some delays, but we will be able to further grow and develop the industry. But when we see many problems here, the Japanese industry as a whole would be in a highly risky situation, a precarious situation. Now, this slide shows what I have been explaining. The semiconductor technology, what is Japan's position against the world? On the top, you can see TSMC, IBM, Intel, Samsung. In the 2020s, in the 2-nanometer chips, we are coming into this range, and everyone is fiercely trying to develop and ramp up. The mass production could be started from next year. In Japan, Renesas had been advancing 40 nanometers, but it has been stopped there. And in order to complement this, TSMC and the Japanese user companies have come together to establish a new company in Kyushu called JASM. So 28 nanometers or 22 nanometers or even going beyond that. But the 2-nanometer level that everyone is trying to go for, the Japanese companies are far, far behind. So for us in Japan to try to develop and manufacture in Japan the 2-nanometer chips would mean something of a survival for the Japanese industry and Japanese economy as a whole. Turning to the next slide. And as you can see, on the left-hand side top, this is the illustration of the supply chain. On the top, you can see all industries. Industries as a whole will be digitalized. And what would be the key technology is semiconductor. Semiconductor would be the basic technology that would be needed by every industry. And if the trade is smooth for chips, then that's fine. No problem for the industries. But when we look forward, there could be some difficulty to be encountered. So there are some opaqueness looking at the country, the state, and the industry. There could be many constraints in the relationship. And in terms of supply chain, if something happens in one country of the world, the materials and parts and components, the flow of those could be stopped or stymied. And we also have problems of climate change and other global issues. And if as situation progresses as is today, then the whole world, the Earth itself, will be in danger. So these are many challenges and problems that we need to overcome, and we need to develop technologies to bring solutions to these issues, if possible, in Japan as well. And this is the high-speed semiconductors, low-power semiconductors mentioned towards the right, and the networks, and also edge and so forth. We need to strengthen all of these technologies by the state as well as the private sector. So the capability and competitiveness of the industry needs to be strengthened, and with the help of the state. And we would like to make this happen with all the efforts to be undertaken. On the left-hand side, you can see this illustration, which depicts how the deepening of the artificial intelligence is progressing, and it is exponentially growing with exponential speed. We often use the term singularity. It would go beyond the human brains or the brain, collective brain of the whole mankind. AI could eventually surpass that. And as I have been mentioning, the economic security, geopolitical risks need to also be contemplated. So I would like to make Rapidus a huge success because of all these reasons. And as you can see with this illustration, not just the front-end process, but the front-end plus the back-end and packaging, all included, and also design. Of course, we will not do the design ourselves, but we need to have a capability to support the designing segment. We need to support our customers, and we need to acquire all these capabilities, and that is what Rapidus is aiming for. Now, what is happening in the United States? In New York, there is New York Creates. In Albany, as a center, we have leading-edge industries and leading-edge technologies being agglomerated. And the 2-nanometer technology that we are aiming for will be developed, have been developed in Albany by IBM through this New York Creates, and we would be provided the technology from IBM, the New York Creates. And we would like to emulate New York Creates in Hokkaido, what we can call Hokkaido Creates. That's to say, the basic infrastructure, basic technology, the foundational technologies need to be fully established as infrastructure necessary for our industry. As you can see with all these photographs, all the engineers and technologies and the businessmen all will be gathering from all over the world in Hokkaido. And not only foundries and industries, but also hospitals and universities, research centers, and everything need to be concentrated here. And we need to be given support from the local community and especially from the government. And we would like to move this Hokkaido Creates forward. Of course, it cannot be built overnight, but we will continue to make efforts to make this happen. This is a plan of Rapidus Corporation. And as you can see, in 2027, we have established ourselves in 2022, and this is March 2025 right now. So we have been going through the different preparatory phases. We have been working with IMEC as well as New York Creates. We have been able to strengthen our technological alliances. And in terms of equipments, in December last year, on the 25th, as a Christmas present, we were provided the EUV, the AMSLs, cutting-edge lithography equipment has been delivered. And with this, up until the end of March, about 230 of those equipment units will be installed at Rapidus. And then we will start operating the pilot line, and we will produce samples so that our users, customers, will be able to use those products. And then we will further move forward with a ramp-up. And at the early 2027, we will be able to begin the mass production. This is the speed we are trying to move forward. Without this fast speed, I don't think we will be able to catch up the other companies in the world. So I would like to solicit your kind support and cooperation. This is in 2023. In September, it used to be totally green field. We have started from groundbreaking, and this is 2024. Last year, in December, in just 1 year and 3 or 4 months, so we have come this far. And the equipments are now being able to be brought inside. And half of this building has been already developed as clean rooms, and we have brought in the equipments. So it is almost complete, and this is the latest picture. And in the near future, we will be able to show the completed. This is EUV from ASML. This is a video showing that the equipment is being installed. This is EUV in purple. This is not really visible by human eye. So we use, because it is extreme ultraviolet, so we have put a color on, so you will be able to see. So this is the world's cutting-edge equipment in lithography. ASML, in December last year, the equipment that we purchased is now being shipped from ASML. It is a very large equipment. So in jumbo jet, about 3 units of jumbo jets, that the big mass has been partitioned up to be sent over to Japan. And it has air conditioning installed in the container to be shipped to Japan. And the ASML staff are sending off their equipments.
And then the equipment were loaded onto the airplane, and this is when the airplane landed on the Chitose airport with snow. And this is how the plane landed. And I was very, very impressed watching that. For Japan too, such leading-edge equipments are necessary for mass production. However, this is the first time that Japanese companies installing and introducing such a big machines for chip production. So we are quite nervous. We had to take care in transporting the system, and the road were with ice and frozen. Therefore, it was transported at a low speed into our factory. This is a picture when the system arrived, and we had our employees together, and we had a simple ceremony with cake and coffee. We celebrated the arrival of the system. And at the bottom right, you can see Koike-san, the president of the company, and he made a greetings and cut the tape. Next. And as I have been saying, the AI is deepening and deepening very fast. And we are here, and it says AGI, ASI. ASI S stands for super. So how can I say, artificial super intelligence, that is a ASI, that is beyond human brain capability. So at the top, God-like AI, it says. So it is very, very overwhelming capability. So to that extent, when AI advances, computer power is very much in demand. In the past, so far as you can see, we had a Moore's law. It is often used for miniaturization rule in semiconductor. It takes 2 to 3 years to double miniaturization. So that was the Moore's law speed. So by the same token, computer power has increased. That was what we have seen so far. However, after 2010, exponentially, computer power increased. So on the top right, you can see 3 to 4 months. It takes only that short period to double. Therefore, the scale is completely different this time. So this is how computing scale power is increasing. So in that case, the power consumption will be a challenge. So this is the power consumption at data centers. So if we compare 2018 and 2030, about 17 times power will be consumed only at data centers. This is only example of data centers. So to that extent, power consumption will grow. So maybe we can do away with using power. No, it's not the case. Therefore, we have to consider how we can reduce power needed. So next page, please. So 40 nano to 2 nano. So nanometer is 1 over 1 billion. So that is a nanometer. So 2 nanometer is extremely small, miniature. Compared to 40 nano, the power consumption can be reduced by a factor of 20. So that is a characteristic of 2 nano chips. So compared to 7 nanometer, it can come down by a factor of 4. So we can make efforts to reduce power consumption, but at the same time, technically, by using technology, we will be able to scale down the power needed. We will be able to reduce power consumption with technology as well. Next, this is what we are going to do in terms of technology. Earlier, I talked about the front-end processing, and I talked about the circuit width. And this is about packaging side. Now, we used to call the planar packaging. This is the conventional technology, planar one sheet. And gradually, this will be stacking up vertically. Now we are at the 2.5D. So computing, that is a calculation part, and also a memory side. At the 2.5D, they are separated. However, they are stacking upward. But in the case of 3D, computing part and memory layers, they are connected vertically. As a result, computing part and memory part, between the two, the electron will moving very quickly and smoothly. As a result, power consumption can be cut down to 1/10 compared to 2.5D. So this is extremely important technology. Next. And if we look at market side, the general purpose CPU was used. Therefore, the device can cope with everything. That was important. However, now CPU plus GPU is used. This is again general purpose device for processing. However, if you look at where the device is actually used, we can see dedicated use chips for medical use and robot. So we have the chips specific to a domain of use. So specialization of our dedicated use chips will be more in demand in the future. As a result, in the past, we were using general purpose. Although chips can do everything, however, when chips are used, we can understand most of the functions are not utilized. However, such chips or devices use up a lot of electricity. However, we can limit the part only usable, only useful, so we move to specialization or dedicated use chips. So as a result, we can reduce power consumption by 1/5. So technology, market, and all these elements are important in order to reduce power consumption. This is how we are seeking lower power consumption through market and technology innovation. So in order to realize that, I talked about miniaturization earlier. Next page, please. In the past, the manufacturing process has become very much miniaturized. That was very complex. Therefore, the mask form, geometry had to be taken care of at design stage, so that we can compensate for complex manufacturing miniaturization. That's how we try to use DFM, design for manufacturing. But what we are now seeking is as follows. Design space, design side is getting more and more complex. And also, delivery time is about as long as 2 years, and it is very costly now. Therefore, from the manufacturing side, we would like to help design side. From the manufacturing side, we want to make a design process more simple. So manufacturing for design concept will be utilized. So this is what we call DMCO, Design Manufacturing Co-optimization. So this is the technique we are going to use at our factory. Next. Particularly in the case of Rapidus, speed is the key. This is what differentiates us. I talked about dedicated use chips, and this is about customization. When we want to customize, the speed is the key. From development to manufacturing, how much time could we save is the key. Design solution, front end, back end, all of this as a whole has to be shortened as a cycle time. Currently, because of the horizontal division of labor, that between the each processes, there is a silo barrier. We are going to remove barriers between these processes so that design solution through back end, we are going to smoothly and efficiently cycle all this process so that we can achieve a short total cycle time. So the key concept to achieve this is a single wafer technology. What is that? In the past, we used batch time. So 100 and 150 wafers are put into the same process. So that part was mixed in the total factory environment. The problem with this is 100 and 150 wafers in a batch to be processed. Data collection would be quite difficult. In the case of heat treatment, the several hours, 5 to 10 hours at maximum would be necessary. To that extent, the amount of data we can collect a day was quite limited. And furthermore, 100 wafers of batch, wafer process, whether or not there is a uniformity among these different wafers is very difficult to see. Therefore, we use single wafer, so we can collect the data from single wafer one at a time. So we collect a lot of data, and we can make manufacturing more efficient. And also, this will contribute to speed as well. So with such a way of production, we are going to achieve speed too. This is one example. This is in the case of single wafer style compared to the 100 wafers, we can get silicon data of 100 times. And within the factory, silicon big data, as we call it, we are going to collect and store silicon big data at the factory, and that would fed forward to design side. So with that, MFD, manufacturing for design, as you can see on the right. So in processing wafer, in that process, window can be expanded. Process window is expanded, and also design margin can be contained or limited. So that will be made possible based on the data to be collected. With this, data processing will be made more speedy. So this is the cycle we can achieve. So what kind of model is it? Historically speaking, in Japan, in the past, IDM, integrated device manufacturer. So there was a vertical integration. Everything needed to be done in a factory of our own. However, that has shifted to horizontal specialization. So like specialization between Taiwan and the US. So at the global level, horizontal division of labor proceeded. And then foundry, fabless, and design house, and packaging house. So they are specialized in their own work. So again, at the beginning of this process, it was very efficient and effective. And because these companies are well specialized, however, conversely speaking, we introduce barriers between the different processes. Therefore, once again, we are going to integrate this. Just simply integrating, we are simply going back to past IDM model. Therefore, we call it RAMS. IP, R&D, EDA design, material and equipment, and all this will be integrated through international collaboration so that we can reduce cycle time. This is the model we are going to use. So as you can see, R&D, IP, EDA, material, equipment, this is on the side of Rapidus, but through collaboration, in relation to customers, we are going to speed up cycle time, and we will be able to feed back or feed forward our data to our customers many, many times so that we can accelerate system development on their part as well. So this is going to be our lifeline, and this is going to make our factory different.
Now, it is not Rapidus will go forward on our own or alone, but for Rapidus to see sustainable growth ahead of us, we need to have a broad basis to support the whole process. So LSTC, Leading Edge Semiconductor Technology Center, has been established. This is NSTC in the United States. So this is the Japanese version of NSTC. We call it LSTC, and LSTC will support Rapidus Corporation, but not only Rapidus, but be able to support the semiconductor industry as a whole in Japan. So when it comes to research and development, not just 2 nanometers, but beyond 2 nanometers, so we are moving forward through international collaboration. And at the same time, we need to build more ecosystem. We need talents to be developed. We are working with universities and different institutions. We are planning ahead. We are also working with the high school level professional or the vocational schools to try to develop engineers and technicians. And we are not looking just inside Japan, but we're looking at Asia as well as Europe and the United States. So we will be working with all these different countries in trying to establish an ecosystem to build the necessary human resources. So we would like to move forward with the international collaboration to try to strengthen supply chain with the LSTC also included to create a new supply chain, if you will. We need to have human resources development. Talents are assets, treasure for us. So we need to educate people. We will work with the United States as well as India and the Asian countries and European countries and inside Japan. As Tensorent is mentioned here, we will be working with these institutions and companies. We will also be working closely with Japanese universities and also universities outside. The 8 major universities are particularly working closely with us, and we would like to multiply these numbers. And with this as a foundation, we would like to have international collaboration with universities abroad as well. And if we can think about success of Rapidus, then education matters very much. So we need to make investment into talents, human resources development, and not only making investment, but we need to create wisdom for the whole mankind. We need a good conviction, an ideal to promote such wisdom for the whole mankind. So we will have human resources and technology input, and in a very quick process, we would like to bring forth innovations. I very much hope that Rapidus will be able to contribute in this regard, and I would like to once again solicit your kind support. This is Dr. Clark. Boys be ambitious was the phrase that he has encouraged the students in Hokkaido. So, Rapidus be ambitious will be our slogan. Thank you.
Thank you very much, Mr. Higashi. In the remaining time, we would like to take up questions from the floor. If you have a question, please raise your hand.
はい、じゃあお願いします。
グレン福島と申します。今日は大変 Thank you very much for very interesting lecture.
私は40年ほど前に
I was working at the USTR office, and I participated in the Japan-US Semiconductor talk and Cadence EDSA. I was serving as the president for 4 years or so, up until a year ago. It was very interesting. Now, I would like to
今アメリカでそのCHIPS Act という形で半導体製造努力をしてるんですが、一つの大きなこれ人材で、アメリカはその先ほどスライドにありましたように40年前は非常に半導体設計製造したんですけど、今はそのスタがあまりにも少ないというので、アリゾナとかTSMC の投資のアリゾナとかあるいはオハイオとかですね、インテルでも非常にその人材不足というのが最大のネックなんですが。
people. In the case of Japan, concretely, you talked about human resource development collaboration, and more specifically, in what way with Japanese universities, chip design or manufacturing engineers are being nurtured? In what concrete way are you doing the effort in the area? Also, foreign talents, to what extent is Rapidus ready to utilize foreign talents? What is your talent plan?
将来の人材ということになるかと思いますが、現在はですね、
毎月30人から40人、毎月ですね。日本の半導体のエンジニアが入ってきている。これは1990年代、先ほど日本が 50% シェア取りましたけども、その頃に半導体に身を投じた方々が世界一の半導体をやるということで、今ラピダスの方にどんどん入ってきているという状態でありまして、当初始めたのは12人から始めたわけですが、今600人を超えているということで、年内には1000人を超えるような規模になる。ここら辺はいわゆる最後のチャンスに間に合った現状いろいろやっていく上でですね、いうところでありますけども、おっしゃるようにその先が非常に重要ということで、先ほど来LSTC でやっているという話言いましたけども、東大はじめ東北大、名古屋大学とかですね、阪大も入ってますし、東京科学大学、そういうところも入って北海道大学、そういう形で、今は8社、これにさらに横浜国大とか私立の大学とか、そういうところも加入してもらってですね、いわゆる半導体、こういう半導体やるためにどういう技術が必要であるかというカリキュラム、これを今みんなで考えているところですけども、これを全国的に使える状態にする、共有していくというような形の構想を今考えています。でこれにはもちろん高専も入っていただくということで、これ文科省、それから経済産業省も中心になってこれやろうということで考えています。であと海外の場合にはですね、特にアメリカの方ではカリフォルニアの方に設計拠点を作りましてですね、そこに今人を集めているというところで、特にアメリカでは設計開発が強いわけですから、その人材をカリフォルニアに集めるということでやっています。そういうような工夫とか、あとヨーロッパ、あるいはヨーロッパでもいろいろ研究機関なんですが、研究機関が同時に教育機関でもあるというところがありまして、そういうところと連携したりですね、あるいはインドなんかともいろいろ一緒にやっていこうということで話を始めています。ですから後半にですね、そういうようなことで、いわゆる日本だけで固まった場合には明らかにある意味では人材が非常に足りなくなってくるということを、いわゆる世界的な形で考えている。その代わりですね、このラピダスは日本のためだけじゃない、世界のためにやるんだということでやっていかなきゃいけないという具合に考えています。
Thank you.
以上です。ありがとうございました。ありがとうございました。
Any other question?
読売新聞経済部の小野田と申します。本日は貴重なお話どうもありがとうございました。経済報道に携わるに関しましての半導体産業の動向というのは大変関心を持っております。その半導体産業ですけれども、極めて細分化されておりまして、たくさんのプレイヤーがそれぞれにいらっしゃるというふうに理解してますけれども、ラビダスさんはその設計、前工程、後工程、全てに関して取り組まれていきたいという話です。でこれがうまくいってですね、その IBM に生かした IBM にならないとなった場合にですね、一つの工程に取り組むよりもですね、その収益面、競争の優位性、それからサプライチェーンの強化、寄与度、これがどの程度ですね、効果が見込めるかという目安がございましたら教えてください。もう一点が先ほどもお話ありました人材の育成ですけれども、その技術者のみならずですね、その優秀な技術者に来ていただくために、その指定まで含めた教育といったインフラっていうのはですね、必要になってくるかと思うんですけれども、今の製造拠点の周囲にですね、そういったインフラが必要なものがあるとすれば、どういったものがありますか。それも教えていただけませんか。
まず技術面ですよね。で考えた場合に、先ほどアメリカの話も
しましたけ
Now
ど
about
も、
technology.
我々もやっていく中で非常に気がついたんですが、
mentioned about the
その
United
日本の
States.
中でやっぱり設計とか開発の部門というものが非常に不足
Now,
し
as
てい
we
る
were moving
と
forward,
いうのが
we
ありました
have
もんですか
come
ら、
to understand
まず
that
最初にアメリカ
the
にですね、
design and
この設
development
計開
is
発
what is
拠点を
lacking.
作って、
These are the
そ
segments
こでの
lacking in
人材
Japan.
を
So
活
that
用
is
し
the
てやってい
reason
かな
why,
きゃいけな
first
い
of
だろ
all,
うという
we
形
have
で
established
考
our
えて
operation in
動
the
いている
United States
と
for
いう状態
design
であ
and
ります。
R&D.
で、
So we will be
資
able
金
to
的に
utilize
考えた場合
the
に明らか
existing
にですね、
talents
今
available
我
in the
々
United
は
States.
現状で
So
は
that is
自分
why
たちで
we
お金
have
を生み出せる状
established
態ではないと。
our
まだ
operation in the United
これから
States.
製造が始ま
But
る
in terms of
という
funding,
ところですので、
right now,
この
we are not able
このラピ
to
ダスの
have
日本に
enough
とっての
funding
意味、
ourselves
世界にとって
because
の意味
we are
というもの
not
をです
yet
ね、よく説明
started
しなが
the
ら、
manufacturing
国のレベルでの
So what would be the
いわゆる
relevance
協
and
力をやる
meaning of
というとこ
Rapidus
ろがまず第一にある。
in Japan as
それか
well
ら
as in the world?
第
We
二は
need
で
to
す
explain
ね、これからいわゆる
and
民間の
trying
方で
to
も
gain support,
どういう技術が必
especially
要
from
で
the
ある
government.
というようなこ
That
と
was
をお
very
互いにベー
important.
ス
And
いろい
secondly,
ろ考えながらです
in the
ね、
private
その
sector
必
as
要
well,
な技
what
術
would
を
be the technology
ラピダス
which will
で
be
やっ
most
ていけるとい
needed?
うことをベ
We
ース
need
に
to
しながら
consult with each other,
投資もしていただくと
and for
いうような
such
ことを考え
necessary
ています。
technology,
で、そこでも
if
う一つ
Rapidus can
重要なことは
provide
ですね、
some of that,
我
we would
々
like
ラ
to
ピダス
ask
は
the
前工
private
程の方
sector
では2ナノ
businesses
メータ
also
ーということで
in us.
限定されるわけですけれど
And
も、
what is also
いわゆるパッ
important
ケージ
is
後工
in
程の方
front
ではですね、
end process, we
い
are
わゆる
going
2ナ
for
ノ
2
メーターだけじゃなく
nanometers,
て
so
い
it
ろん
will
なデ
be
バイス、パワーデバイスもあ
limited
りま
for
すし、
that.
そういう
But
もの
for
を
the back
組
end,
み合わ
the
せた、
packaging,
先ほど 3D って言いましたけれど
not
も、
just
そう
going
いうよ
for
う
2
なパッケージン
nanometers,
グで
but we need
産
to
業
think
に対応
about
できる。
different devices,
2
power
ナノメーターは
device
その
and
一部
others.
と
I
いうよ
have
うな
mentioned
形
about
で、
3D.
そういう産業への対応力というも
We
の
will
も
be able
ラピ
to
ダス
have
の中で持っ
diverse
ていく。
packaging
あるいは
for
その
the
サポートっていう意
customer
味で言います
industries.
と
And 2
LSTC の方
nanometers
でも
will
サポート
just
して
be
いく
one
というような
of
ことを考
such
えています。
available
そこら辺が、
So
今
in
我々
terms
が
of
考えている
support,
ことでありま
the
して、
LSTC
その
will
国
continue
の
to
レベ
support us.
ルでいわゆる近いレベル、5年とか10
So
年ぐ
these
らい
are
の
the
レベル
things
です
that
と、
we
や
are
はり
thinking right
経済
now.
産業省様からのいろいろな資金的なサポートと。
Now,
いうものが
about
重
the
要でありま
government
す。
level,
それ
in
は
terms
やは
of
り
5 years
産業化、
or 7
事
or
業
8
化ということを
years,
ベースにしなが
Ministry
ら
of Economy, Trade and
予
Industry
算をいただくと
will
いう
be
形になり
providing
ますが、
us
もっと長期的な
financial
話にな
support,
りますと、
and
文科省と
we will
いう
do
こ
our
とで、
best
文
to
科省と、
commercialize
そこら辺の話を
our
今、
businesses
予
to
算取り
be
も
able
含め
to
てですね、
gain
やっ
the
ていく。
budget
これは
support from METI.
ラピダス、
And for
あ
much
るいは
longer
LSTC
term,
っていう枠
we are
を超
also
えて、
discussing
各大
with
学、各研
Ministry
究
of
機関にそこのお
Education,
金を落としてい
including
た
the
だく
foundries
というよう
and
なこと
training,
で考
going
えている。
beyond the framework
いうと
of
ころであります。
Rapidus
答えになって
Corporation
ますでしょうか。
or the LSTC, we would like to have
ありがとうございまし
universities
た。
to work
他に
closely
ござい
with
ますでしょう
us.
か。
So some of their budget could also be provided for us.
はい、
Does
そろ
that
そろ予
answer
定
your
の時間が
question?
参りましたので、
Thank you.
これで、
Then
講
any
演
other
会を
question?
終了させていただきます。東会長、
Thank
本日
you.
はどうもありがとうございました。
I think we are
どうもご
running
清聴ありが
out
とうござい
of
ま
time
す。
to end. So with that, we would like to conclude the meeting today. Mr. Higashi, thank you very much.